Hello friends, welcome back to my channel. So this is part 3 of Hui book and we are going to discuss in it various type of bonds. We all know that how this covalent bond and ionic bonds are formed. We will not go in the detail of these type of bonds, but we will see certain different type of bonds, right? And then we will compare the strength of these bonds and certain important formulas which will help us in solving questions, right? Then we will take few questions related to these bonds and then we will start molecular orbital theory. I will not cover the complete molecular orbital theory in this chapter, in this video, because it is not possible to cover that in single video. So I will just start it today and then we will complete the theory, right? And first type of thing is, so the first type of bond we all know is electrostatic bonds, and you can call it as ionic bond. We all know that how these bonds are formed, right? And we know that this energy of this type of bond can be given by bond-Length equation, but if we are not considering the repulsion part of that, so this energy is simply inversely proportional to R, right? Energy is inversely proportional to R, and this electrostatic bond or ionic bonds are non-directional in nature. This point is important. You should know that these bonds are non-directional in nature, but at the same time the covalent bonds are directional in nature, right? And we can classify these electrostatic bond and covalent bond into the category of chemical bonds, and the bonds which we are going to discuss can be categorized into physical bonds, right? Physical bonds. So first we are going to take ion dipole interaction, as it is clear from the name that this is the interaction between an ion and a dipole, right? So suppose I am dissolving NaF in water, so this NaF will break into Na plus and F minus, right? Now this sodium plus will water molecule around it. This oxygen will have a negative, partial negative charge, and this is the interaction between opposite charges, right? So this is ion and these are dipoles. These water molecules are dipole. Similarly, if you have here fluorine, then H part of this OH will interact. It will have a partial positive charge, right? So we will have these type of ion dipole interaction. So we are taking here a ion, suppose this is Z plus, and we have a dipole here which has a negative charge close to this positive charge and positive charge is away from it. So this is the distance between these two charges of dipole. This is suppose R dash, and we can denote these charges by Q minus and Q plus, and this is the distance between this ion and dipole. It is denoted by suppose R. So this energy of this interaction will be given by the charge on the ion, that is Z plus. So the energy of this interaction will be given by ZeQ over 4 pi epsilon naught R, right? And this Q can be calculated from the dipole moment of this dipole. This is QR dash, and from here we can calculate value of Q. It will be mu over R dash, and when we will place it into this equation, it will become, we can consider these two distance almost equal, so suppose it will become R square. So I am taking only the simple equation here, and this energy of interaction is inversely proportional to R square. This thing is, the simplification is only done to explain this thing, that this energy is inversely proportional to R square. R square means this R is an inverse of this energy. So this energy, this interaction, this ion dipole interaction is weaker than electrostatic bond, because in case of ionic bond, energy is inversely proportional to R. Now it is inversely proportional to R square, so it is further decreased. So this type of interaction can be seen in this type of that when you are dissolving ionic compounds into polar solvents. Then second type of interaction is dipole-dipole interaction. It is between two dipoles which are already dipole, and their energy is inversely proportional to r cube, means it is further lower than ion dipole interaction. Then third type is permanent dipole and induced dipole interaction, means one will be permanent dipole in nature and in other one the dipole characteristics will be induced, right? So you have HCl and chlorine supposed together. So HCl is already a dipole, and when chlorine come close to it, then two chlorine atom will be like this, suppose, and one chlorine will become partially positively charged and other will become partially negatively charged. So this dipole is induced in the chlorine due to the presence of this permanent dipole. So you can have permanent dipole and dipole characteristics will be induced in a dipole, or you can have ion and induced dipole interaction, then energy will be inversely proportional to r to the power 4. And when you have dipole, permanent dipole and induced dipole interaction, then energy will be inversely proportional to r to the power 6. So this should be very clear. Question can come in on this type of things, so please be clear about them. Next type is, that is fourth one, is London forces, which is also called as instantaneous dipole and induced dipole interaction. So this is very interesting, that in a starting your dipole is, the molecule is not dipolic in nature, right? And it develops dipolic characteristic instantaneously, then it will induce dipolic character in other molecule also. So this, the main example of such type of interaction is observed in noble gases like helium, neon. So when these gases are in this form, these atoms of gases are in this form in a container, suppose, so they should repel each other. But what happens that when they come close to each other, induces dipolic characteristics in them, right? And they will interact nearby molecule, which will also induce dipolic character in them, and they will have very weak bond between them which held them together. So this type of forces are called London forces, and they are very weak in nature. The energy of interaction is inversely proportional r to the power 6, right? So on the basis of this energy and its relationship with r, you can decide that what will be your energy order. And these London forces are also called as van der Waal forces. Now you can decide that what will be the correct energy order for all of them. So highest will be given to ionic. Sometimes covalent bond can be very close to ionic bonds, then covalent bonds, then next will be given to ion dipole interaction, because in that case energy is inversely proportional to r square, right? So you can remember them in this sequence only, and then you can remember the relationship of energy with r in the same sequence, that first we have only one power, then 2. You can write down in this way that energy of ionic bond is inversely proportional to r, then energy of ion dipole bond is inversely proportional to r square, then energy of dipole interaction is inversely proportional to r cube, then next you have permanent dipole and induced dipole, which have relationship from r4 to r6, depending upon that you have interaction between ion and induced dipole and dipole and induced dipole, right? This one. Then last you have instantaneous dipole, which is not dipole in the starting, so this is instantaneous dipole and induced dipole. So this is inversely proportional to r6. So you can remember in this way only. Now you can decide that what will be the energy order. First we have ionic, and in between ionic and covalent you will also have metallic bondings which are also very strong. Then we have ion dipole, dipole dipole interaction, then dipole induced dipole interaction, and then you have instantaneous, or you can say directly it as London forces or van der Waal forces, right? And your hydrogen bonding is type of dipole dipole interaction. Remember this one, it is very important. So you will have to place hydrogen bonding in between this, between covalent bond. Suppose you are taking covalent bond and van der Waal forces, so the energy of, or you can say strength of hydrogen bonding will be in between covalent bond and van der Waal forces. They should be greater than van der Waal forces, but sometimes your hydrogen bonding is also comparable or weaker than van der Waal forces. This is for certain cases only, so we will take these cases later in main group elements. We will study about them, right? But in the at this point you can consider this, that your hydrogen bond strength is greater than van der Waal force strength. Next we have hydrogen bonding. So we all know that what is hydrogen bonding, but again I will say that we will take only important points from which question can arise and we may have confusion. So they can ask that hydrogen bonding can be categorized in which category. So generally it is type of dipole dipole interaction. It may be ion dipole interaction also, but you can categorize it into dipole dipole interaction. The energy of hydrogen bonding lies in the order of 10 to 40 kilojoule per mole. Now you can compare that your covalent bond have energy almost, or you can say average is 400 kilojoule per mole. In this way, hydrogen bond strength is 1/10 of covalent bond strength. This is very important, right? They can give you the energy of covalent bond and they can ask you that what will be your hydrogen bond. Approximately you have to give the idea that it will be nearly 1/10 of covalent bond. Then we know that in which type of moieties we can observe hydrogen bonding. We will need basically hydrogen, and highly electronegative atoms should be there: fluorine, oxygen, nitrogen. Chlorine can also show sometimes hydrogen bonding, right? Then next thing is hydrogen bonding can be intramolecular and intermolecular. So this is very basic type of things and we all know that, so I will not go in the detail of that. So if you observe hydrogen bonding in a molecule, then its boiling point should be increased. Mostly in case of intermolecular hydrogen bonding, boiling point should be increased, right? Because in case of intramolecular, the bonding within the molecule, so it will not affect directly to the boiling point. But if you have intermolecular, then it will affect the boiling point of the molecule. And the most important thing is, due to this hydrogen bonding, many gases exist mostly in the form of liquid. The HF exists in the form of liquid due to this hydrogen bonding, right? You can compare directly that H2O and H2S belongs to same group, but H2O is liquid because it has hydrogen bonding, but H2S is gas. There is no hydrogen bonding in case of hydrogen sulfide. So we will see some question that how this hydrogen bonding can help us in determining the order of boiling points. This one. So arrange in order of increasing boiling point. So we have first case where we have taken the hydrides of carbon family. So in case of carbon family, we cannot observe this hydrogen bonding, right? So we have to see that what will be the order of boiling point, and we can decide it on the basis of van der Waal forces. One thing is also should be clear in your mind, that generally in case of ionic bondings, melting point and boiling points are higher as compared to covalent bonding. I am saying it generally, right? Not all the time, but most of the time the boiling point and melting point are higher for ionic compounds than covalent bonds. Means when you have stronger bonds, boiling point will be obviously high, right? Similarly, if you have van der Waals forces among different molecules, then you have to observe that van der Waals force will be stronger for which molecule, and if it has higher van der Waals force, then its boiling point will be higher. Means the strength of van der Waals force will also decide the increase in the boiling point. And we know that the van der Waals force depends directly upon the molecular mass of the species. If we have higher molecular mass, then van der Waals force will increase and directly its boiling point will increase. So for this example, we have to consider only van der Waals forces, and the force will be highest for the species which has highest molecular mass. Means the order of van der Waals forces will be like this, that lead hydrate will have highest van der Waals force and directly its boiling point will be highest, right? You can write down that it is directly proportional to boiling point. So this is very simple for such type of cases when there is no other type of bonding can be take place, right? Then we have next is oxygen family members, right? You can say hydride of or oxygen family. Now we cannot apply the same thing here because we have water here and it will show hydrogen bonding. So we can apply the theory of van der Waals forces for these three, right? And we know that hydrogen bonding is stronger than van der Waals forces, therefore boiling point will be highest for water. So we have to first separate this one. Then we will see the order of van der Waals forces, means it will be highest for highest molecular mass species. So next will be for tellurium, then we have for selenium hydride, then we have H2S. So this will be the order for oxygen family members, right? Then we have this halogen hydrides. So again the same thing will be applied, that here we have hydrogen bonding and here we have to look for the van der Waals forces, right? So highest boiling point will be for hydrogen fluoride, then Hi, then HBr, and last, or you can say smallest boiling point will be for hydrogen chloride. The last example is very interesting. I have seen a number of questions based on it in IIT JEE level, right? So I have included it here because I consider it is important. So we will see here that they don't belong to the same group, right? So we cannot decide on the basis of it. We will have to decide on the basis of only hydrogen bonding. So first we will see that in case of methane there is no hydrogen bonding, so it should be placed in the least corner, right? And next will come for ammonia, because we are deciding it on the basis of electronegativity. The hydrogen bonding will be directly proportional to the electronegativity of the atom, right? For the most electronegative, hydrogen bonding will be higher. Now next question comes that hydrogen bonding will be stronger in water or in HF. So on the basis of electronegativity, it should be strongest in HF. So we should place HF on the highest order, means its boiling point will be higher, then it should be for water. But if you look at the molecule of HF, there is only one fluorine, or you can say only one electronegative atom, so there will be only one hydrogen bonding. And in case of water, we have two hydrogens. Here we have only one hydrogen bonding, and here we have two hydrogens which can participate in hydrogen bonding, right? So there will be two bonds. So the hydrogen bonding will be stronger in case of water than HF. So boiling point will be higher for HF than for H2O than HF. The next thing is structure of copper sulfate .5H2. So I think this can be an important part. It will take very small time of us to understand it, but question can come on this topic also. So in case of copper sulfate, the structure is very unique. We can think that these all 5 water molecules should be connected with this copper, but the actual condition is entirely different, right? We have this type of structure. First, the copper is directly connected with four water molecules, right? Then next is the bonding with oxygen of this sulfate, like this. Then what is the place of fifth water molecule? It is connected with this one water molecule with hydrogen bonding, and this hydrogen is connected with oxygen with hydrogen bonding of oxygen of sulfate. Similarly, this hydrogen will form a hydrogen bond with the water molecule of other copper atom, right? It will form hydrogen bonding like this. So in this way, only four water molecules are directly connected with copper, and one is connected with hydrogen bonding with water molecules of copper and sulfate. So this is very important question, that only four are connected with oxygen with copper and one is connected by a hydrogen bonding, right? So in this way, its structure is distorted octahedral in nature, distorted octahedral geometry. So question can come on this also. Then we have next hydronium ion. So hydronium ion has dodecahedral type of structures, and they form clathrates when they go in solid form. Clathrates are basically the cage type compounds which contains generally ideal gases in the center, in the cavity of them. So we will take that part in next chapters when we will discuss cage compounds and cluster compounds. So I will not go in the detail of that part in this video. We will next take molecular orbital theory. It is part 1. We will take only few part of it in this video, then we will cover it in the next part. So I will tell you only the important points here, right? We all know that what are the assumptions of molecular orbital theory and why valence bond theory fails, and then why this molecular orbital theory arises. We have studied that part in many books and number of times, but now I will tell you only the important points about that. So first thing which is very important about molecular orbital theory is that all the atomic orbitals of one atom will mix with, or you can say overlap with, all the atomic orbitals of other atom. This is very important point, because in case of valence bond theory, only valence atomic orbital, the valence electrons participates in bond formation, but in case of molecular orbital theory, all the atomic orbitals of one atom will mix with all the atomic orbital of other atom. This point is very important. Then next point, we all know that atomic orbital will mix together to form molecular orbitals, right? And number of atomic orbitals is equal to number of molecular orbitals. Next point is, this mixing is due to linear combination of atomic orbitals. So we will see that what is the linear combination of atomic orbitals a little bit later. Then next point is, which is important, I am taking only here the important points. The several assumptions were taken when this molecular orbital theory is formed, but I am taking only the important ones which will help you in solving your questions. The next point is that when the atomic orbitals overlap or mix together, means they will not directly go and mix with each other. Actually, their wave functions will mix together, right? When we are talking in terms of quantum theory, the wave functions of atomic orbitals mix together to form wave functions of molecular orbital, right? So this mixing of wave function can be done by two processes, that by constructive interference, or it can be done by destructive interference, right? You can consider constructive interference when we are thinking about waves when they mix together in same phase, right? In same phase, when they mix together, there is total increase in their wave function, there is something constructive in nature. And destructive interface means when they are mixing in opposite phases. If they are mixing in same phases, means same direction, they have positive phases together, it will give you positive. And when they are mixing in opposite phases, they will give you nothing, almost nil, right? There is nothing generation. So in this way there is two type of mixing of wave functions, and when they mix in constructive way, when they are increasing the wave function, or you can say increasing the electron density increases when they mix in the same phase. So this type of bonding will cause bonding molecular, will form bonding molecular orbital. This is just starting of this theory, right? I will tell you that how this bonding orbital molecular orbitals will form, but this is just beginning. Then if they are mixing together in destructive interference, their electron density will decrease, right, and they will form anti-bonding molecular orbital. Then we will see that how this electron density will decrease and what will be the energy orders of this bonding molecular orbital and anti-bonding orbital. We will see it little bit later, but this is the few steps which you should know. The next important point is that when you are filling your atomic orbitals, then you follow certain rules: Horn's rule, Pauli's rule, Offer rules. You all know about these rules. Same rules will be followed here. Horn's rule, Pauli's excursion principle, then your Offer principle, all will be followed here also. Filling will be take place according to these rules again. So when we will fill electron in molecular orbital theories in upcoming chapters, in your upcoming videos, we will follow all these rules. Then I will tell you that how we are following these rules, right? There I will tell you that at this step we are following these rules. So we will see all these steps one by one in our videos. We will see all these things in upcoming videos, and this is very very important, because if you don't know the basic of a theory, then you cannot solve a difficult question, right? So this should be very clear in your mind that what type of things are going to take place when we are constructing a molecular orbital. The next point is, what is this? So we know that number of atomic orbital will construct to form same number of molecular orbital, right? Remember this point. Then we will see that what is this linear combination of atomic orbitals. So we should know that on which concept your this linear combination of atomic orbitals depends. First thing is the orbitals which are going to mix together. Suppose I have a s orbital here. It has positive wave function. Its phase is suppose positive, means in all direction it has same type of phase. Then we have another s orbital. They will mix together, suppose overlap together, and they will form a new molecular orbital. They will two atomic orbitals, then they will form two molecular orbitals, right? Two molecular orbitals will be formed. In one there is constructive interference and it will lead to generate bonding molecular orbital. In other one there is destructive interference and anti-bonding molecular orbital will form. So we will see that what will be the structure of this bonding and anti-bonding in next part. First we will take that what things decide that they are mixing this linear combination, their combination will take place or not. So first thing is that they should have same symmetry. Their symmetry should be same or almost same, right? So s orbital can mix with s can mix with pz, but s cannot mix with px or py, right? They have same different type of symmetries. This is your s, and when you will mix it with px and py, so this is positive and this is negative, these two will cancel each other and there will be nothing, right? So this type of mixing cannot take place. In this way you can mix it. This is positive wave function, this is positive, so this type of mixing can take place, but the orbitals which have different type of symmetries cannot mix together. Then the energy gap between atomic orbitals which are going to be mixed together, energy gap should be minimum, right? If we have almost same energy atomic orbitals, if they are of same energy, then their mixing will be almost complete mixing, right? And if they have very high, when they have low energy gap, then they have partial mixing, right? But if they have very high energy gap, they cannot mix together, so the energy gap should be minimum between them. Then we will see type of LCAO mixing. Two type can be possible. One is head to head mixing, and it will lead to the formation of sigma molecular orbitals. And another one is side wise over mixing or overlapping, and it will form pi, delta and phi molecular, right? There are two type of LCAO mixing. First we will see that how these sigma molecular orbitals will form. First we will take formation of bonding molecular orbital due to mixing of 1s atomic orbitals. This is very basic thing, that this s orbital which has positive phase will combine with the positive phase another s orbital. These two will mix together by constructive interference. This is very clear, should be your mind. Constructive interference, like that, suppose they are wave function, this is positive, this is negative, and the another atomic orbital will also have same wave function, right? So these two will mix together and they will mix together constructively, right? So in this way the electron density between internuclear distance will increase. Or you can think is it in a different way, that suppose this is your A atomic orbital, this is B, and they will form molecular orbital by linear combination. Psi A will mix with psi B, right? Now we want to determine the electron density between this internuclear distance, so we have to take the square of it, because we are going to decide that what will be its electron density, so we have to take the square of it. So when we will square it, this whole function will also be squared, and when you will open it, you will see that there is net increase in the wave function, right? So they are mixing together constructively, and this value decides that there is increase in electron density between your internuclear distance. Or another way of looking at this, that suppose the wave function, I have not taken that part here because it should be the part of quantum theory, but to explain you, I am taking it here, that suppose this is the relationship between psi and R. You can see this part in Puri Sharma Pathania, as well as it is given in brief in Hui also. So suppose this is the relationship between psi and R for the atomic orbital A. When it will mix with atomic orbital of B, means these two will come close to each other, right? So you can write it like this, they are mixing together like this. This is the nucleus of these two atomic orbitals. This is for A, this is for B, right? So when they are mixing together constructively, means their wave functions are same, and we will take square of it, so it will be like this, right? So there is net increase in the electron density between these two nucleus, or you can say between this internuclear distance, electron density increases. So electron density increases, and means this nucleus can feel more attraction force than in case of atomic orbitals. This one will also feel more attraction force, and when there is increase in attraction force, potential energy of the system will decrease. We know the relationship between potential energy. When we have this negative force together, then potential energy will go in negative direction, means it decreases, energy will be released, and bonding molecular orbital will form. So the electron density will increase in between two nucleus in this way. So this is your sigma orbital, and due to it was due to 1s and 1s, so we will write 1s here, and because it is bonding, so you can directly write it down like 1s. Another way of representation of it is that you can denote G or U here. So how you will decide that here you have G or U, that we have positive wave function everywhere. So when you go from the center of symmetry in this direction, suppose, you will find the same wave function. Similarly in this direction, when you will go here and in this direction, you will find the same type of phase. So it has center of symmetry, right? So in this way, this will be your Girard function. So you can write it down like this also. But if they are mixing together destructively, means suppose one has positive, here we have negative, we can also write it down here negative, so this wave function will become negative, right? So when they will mix together destructively, then what will happen? Suppose we have in the starting here one wave which has positive value of psi, right? So we will denote it by like this, and other one which is due to this second atom, it has wave function in opposite direction. So suppose like this. So here it will not affect because these two are not mixing together, but in this part these two functions have opposite signs. So when they will mix together, there is net decrease in the electron density here. When we will take a square of it, we will first write only psi square. When we will take a square of it, the net electron density will be decreased here like this. So there is net decrease in the electron density here, means attraction force which is felt by these nucleus will be decreased, right? So when there is decrease in attraction force, means repulsive force between them will increase, right? So net repulsion increases, means energy of the system increases. So when energy of system increases, it will become less stable in nature and it will form anti-bonding molecular orbitals, right? So you can write down this anti-bonding molecular wave function. Suppose we have this one, or you can write it simply like this, that they are mixing together like this, and when we will take a square of it to determine the electron density, then there is net decrease in wave function, right? Means electron density will decrease ultimately. Or you can say that between this internuclear distance there is net decrease in electron density. So you will molecular orbital like this, one will have positive, one will have negative sign, and there is a node passing between these two. Between these two nucleus there is a node where is minimum chances of finding a electron, minimum chances, right? This should be very clear, minimum chances of finding electron. This will be called as node, right? So node is the plane which is passing through internuclear region, and where we have minimum chances of finding a electron. Between it is passing through internuclear region. This should be very, very clear. For node, this is passing through internuclear region, right? So in this way we will have our anti-bonding molecular orbital. And if you will try to find out the center of symmetry in it, there is no center of symmetry. So we will denote it by sigma u ungerate, or we can write it like this. Okay, so we can represent it in this way. So all these things are very basic, we all know about these things, but certain points certain points are very important and can be asked in 2 marks question, right? So you should have these things very clear in your mind, that what is exactly the node is and how these bonding and anti-bonding orbitals mix together. So in next part I will take the more detailed version of this molecular orbital theory. So I will finish this chapter here, and in next part we will see, I will try to cover the molecular orbital theory and then we will move ahead, right? So if you like my videos, please share my videos with your friends, and thank you so much for watching.